All right, so now let's take a look at phase diagram for a one component system. Phase diagram is, oops, sorry. A phase diagram is just a diagram that shows the stable phases of a pure substance under various conditions. So we plot we set up our axes for our chart for the different values of the temperature and pressure, for example. Okay, and for a one component system, um, that means when we're dealing with a pure substance, you can set up a chart where you have pressure on one axis and temperature on the other axis, and the chart is set up so that it would look something like this. This is a common feature of phase diagram for pure substances. Okay, it will typically involve at least 3 different regions. Okay, and they are labeled as gaseous down here, liquid over here, and solid over here. The way you would interpret this is to say that at low pressures, at high temperatures, you would expect, if you were to find a sample at low pressure at high temperature, you might expect that sample to be a gaseous sample. Okay, so any point in this gaseous region would correspond to conditions where you would expect to find the sample as a gas. Any point on this region over here in the solid region would represent conditions where you would expect to find the sample as a solid, and any point in the region here that's labeled liquid would represent conditions where the substance will exist as a liquid. So for example, then if at this temperature and at that pressure, so if this is T1 and P1, if you were to find your sample under conditions where the temperature is T1 and the pressure is T1, then you say that sample is gaseous. Okay, so let's try to relate this to something more familiar. So let's imagine if you have a water sample. Okay, you have water in a beaker. What happens to it? Eventually, you know it's going to dry out because your water molecules are going to leave, right? But now let's imagine you closed your container. Okay, so you have water in an enclosed container. Okay, so your container is closed. You've got water right here. Okay, so molecules are going to leave your liquid and go into the gas phase. So you're going to have gaseous water, and the gas phase, water in the gas phase, will eventually, it would also be water molecules in the gas phase would also go back to the liquid phase. Eventually, you get to a point where the rate at which water molecules leave the surface, or leave the liquid, would be equal to the rate at which the molecules go back to the liquid. And you've established the pressure of the gas that you have here is called the vapor pressure of your water. Okay? Now let's imagine removing everything else outside of this container so that the only thing you have here is water vapor. Okay? Now at room temperature, you will find that the vapor pressure, the pressure of water vapor inside this container is going to be about 23.8 torr. Okay, so that's a vapor pressure at room temperature, 298 Kelvin. All right, so let's see where that would be on this diagram. You would say then that at equilibrium, okay, if let's say this was 298 Kelvin, let's just say this is 298 Kelvin, then this curve right here, which separates the liquid from the gaseous region, okay, a point on this curve at 298 K will correspond to a pressure of 23.8 torr. Okay, the vapor pressure of water. If this was water, if this was the diagram for water. Actually, this won't be the diagram for water because the one for water will have this one leaning the other way. Okay, so for the phase diagram for water, this curve right here is actually going to lean that way. But anyway, the idea is that, okay? So that's how you'd interpret this boundary between the liquid and the gaseous region. That is essentially a plot of the vapor pressure of water as a function of temperature. So if you were going to heat this sample up, then you might find that you will find that the pressure will increase, the vapor pressure. You heat it some more, you'll have a higher vapor pressure. Heat it some more, higher temperature, you'll have a higher vapor pressure. Eventually, when that pressure reaches 1 atmosphere, okay, obviously my scale here is not linear, this is just a qualitative scale, then this is going to be at 373 Kelvin. You've reached what's called the boiling point, the normal boiling point of your liquid. Okay, so let me show you an animation to help you better visualize that. And you can go to phet.colorado.edu. Let's go to Fullerton, treefrog.fullerton.edu. It's a website created by wrong one. Okay, let me see. By Professor Patrick Wagner at Cal State. Let me do a search for treefrog.fullerton.edu phase diagram. And you'll find here. Nice animation illustrating this. Okay, installing shockwave player. All right. So, like I said, this thing right here is your liquid region. This is your gas region. That's your solid region. So if I was going to click on this point right here, okay, that might be a condition where I have a gas, okay, water vapor here in equilibrium with liquid water. Okay, and so here's the molecular view of what's going on. You got your molecules in the liquid and your molecules in the gas at equilibrium. Okay. So what happens if I were to raise the temperature of my liquid? This is an enclosed container. The only thing that you have here is water vapor. There's no air, so it's just liquid water and water vapor. Okay, so that pressure is going to be at 298 Kelvin at room temperature. That's going to be about 23.8 torr. Okay, so that means the force here. Okay, there's actually the force here would have to be 23.8 torr. So this can't be open to the atmosphere, otherwise it's going to the pressure is going to squeeze the gas. Okay, so what would happen now? Since 1 atmosphere is 760 torr. If I were to raise the temperature, then basically what's going to happen is my pressure is just going to be increasing. Okay. And you can see that letter F right there is getting bigger, and that means the pressure of the gas is increasing, so you're going to need more force to keep that gas in, to get that, yeah, okay? So that increases in pressure. What would happen if you were to cool down the liquid, cool down your sample? So the pressure of the gas drops. Eventually you reach a point, what's called the triple point, where you're going to have solid. Okay, so that point where you have the intersection between the three regions, you have a solid water, that's ice, and you have liquid water and gaseous water at equilibrium. That is called the triple point of your water. And where does that happen? Under what conditions? Let's look it up. That would happen at, let me just see. Triple point of water occurs at a pressure of, let's see, it's going to occur at a pressure of 0.6117 kilopascals, okay, and at 273.16 Kelvin. So at 0.01 degrees Celsius, that's what. So once you get to 0.01 degrees Celsius, okay, you'll reach your triple point. And that's actually a very low pressure, way below 1 atmosphere, okay? So that's your triple point. That's characteristic of water. What happens if you cool it some more? Then what happens is your liquid will disappear. You will now have just solid and gas at equilibrium. So this line right here, okay, this curve right here is just the curve that represents all possible conditions, all conditions where your solid will be in equilibrium with a gas. You will find your solid and gas at the same time, gas phase, solid and gas phase of your substance at the same time. Okay, so this is really a plot of the vapor pressure of ice versus temperature. Okay, so this is solid right here, liquid here, gas over here. So that's what happens to your water sample as you heat it. Now, what would happen if, let's go back to about room temperature, and we said that this pressure right here, remember we said it's 23.8 torr, right? That's the vapor pressure of water at room temperature. Now, what would happen if this force outside is actually the pressure outside is actually 1 atmosphere? Then you have, okay, so then I have to go up to 760 torr. So what happens? Everything turns into a liquid, okay? So at higher pressures, at 1 atmosphere, okay, if you were to subject your water to a pressure of 1 atmosphere, for example, everything's going to be a liquid. You'll be in the liquid region. Okay? Now, what would happen if I were to lower the pressure? So just pull this out. What's actually going to happen is, as I move this outward, okay, more water molecules will just go to the gas phase to maintain that vapor pressure. Provided I'm maintaining the temperature, the pressure is going to remain to whatever the vapor pressure is. So at 298, if you maintain this at 298 Kelvin, the pressure will stay at 23.8 torr. But what happens when all of the liquid water is gone? Then at low enough pressure, when all the liquid water is gone, okay, and this is somewhat exaggerated here, then everything turns into a gas. So once you increase the volume enough so that the pressure drops below the vapor pressure at room temperature, then everything turns into a gas. Okay, and so you have a very low you're looking at a very low concentration. For a given volume, you have very few water molecules in there. Okay, so similarly, if I have a gas, okay, if I were to start squeezing that gas, okay, what will happen? I'll be increasing the pressure, okay. Eventually, you get to a point where even when the temperature is constant, even at the same temperature, I'm just raising the pressure, I can actually turn that gas into a liquid. So once I reach a certain pressure, okay, then that gas is going to turn into a liquid. So if this happens to be room temperature, once I hit 23.8 torr, my gas will start turning into a liquid. You're going to get gas and liquid at equilibrium. Okay. If I keep squeezing that, what will happen? If I keep pushing the volume in, I can make the volume smaller, then just more of your gas molecules will go back to your liquid. You will be maintaining the constant vapor pressure at that temperature. Okay. But once you get your molecules too close to each other, as close as possible, a very high pressure, okay, once they get really, really close, then you'll have to exert a higher pressure, okay, And so you will, once you exceed the vapor, the external pressure exceeds the vapor pressure, then everything will turn into a liquid. So once you're past this pressure right here, you go back into the liquid zone. Okay, and when you're there, oops, when you get there, oops, what happened here? Okay, everything turns into a liquid. Okay, so what would happen if I have a liquid and I were to cool it down at constant pressure? Eventually, it cools down enough so that your liquid can turn into a solid. So you get to a point where you have solid and liquid at equilibrium. You've reached the freezing point of your liquid. Okay, and so if this was at if this was 1 atmosphere, then that temperature right there would be the melting point or the freezing point of your substance. So in the case of water, that's going to be at 273.15. Look, it's below the triple point. The temperature of the triple point is 273.16. So if this is at 1 atmosphere pressure, that would be the melting point or the freezing point of water at 1 atmosphere. That's called the normal melting point or the normal freezing point. If you cool it further, okay, if you cool it even further, then everything will turn into a solid. All right, so this curve right here basically tells you then how the melting point or the freezing point depends on the pressure, the external pressure on your substance. Okay, so if you raise the external pressure, the melting point doesn't really change very much. Okay, so that's a very steep curve right there. Okay, so going back to our phase diagram, one thing that wasn't addressed in that animation I showed you is that at a certain temperature, above or beyond a certain temperature, you'll find that you will no longer be able to liquefy a gas by simply raising its pressure. Okay, and how can you tell physically, if you were looking at something and you're raising its pressure at constant temperature, how can you tell that it's actually condensing? The gas is turning into a liquid. You see a drastic change in the volume as we go from a gas here, for example, to a liquid there. As you cross over, you're going to see a big drop in the volume. But that drop in volume gets smaller and smaller as the temperature increases, okay, as you do it at higher and higher temperatures. So beyond a certain temperature, which we call the critical temperature, so this is T sub C, okay, you can no longer liquefy gas, and so if you can pressurize your gas, it would seem like nothing's happening to it. It's just what you have there, okay, is just a single phase system. Okay, so this point right here is our critical point, what we call a critical point. Above that, at pressures higher than that, and at pressures above that, and at temperatures higher than that, this region right here is what you might call your supercritical region. Okay, so what you have here is called a supercritical fluid. Another feature of phase diagrams that's not addressed in that animation is that it's possible for a substance to have different solid forms, different stable forms of the solid phase under different conditions. So here you have this is something that would resemble the phase diagram for sulfur, for example. This is the liquid region, this is the gaseous region, this is the solid region, that's another solid region right there. So point A right here would represent coexistence curve, okay, the condition where you have two solid phases of your substance at equilibrium. Okay, so before this solid phase can melt, if you were to heat it, it will transform into a different solid phase, and it's only when it hits this temperature right here when it actually melts. All right, and you can also have a triple point that does not necessarily involve solid and liquid and gas. This triple point right here, marked D, would be a condition where you have two solid forms and a gaseous phase in equilibrium. Okay. All right. The term variance refers to the number of independent variables that we use to describe the state of a system. In the case of a one-component system, so C is 1, okay, if it has P, the number of phases present in the system is P, okay, and so if you take C minus P and add 2, you get what's called the variance. The F would be C minus P plus 2, and that would be the number of independent variables that you need to define the state of your system. For a one-phase system, one-phase system, if you have one component, one phase plus 2, your variance is 2. What that means is if you only see one phase, let's say you see a sample, it's gases, okay, so there's just one phase and it's pure substance, so one component, then you need two variables, two quantities to define the state of your system. For example, point C right here, okay, it's gas. If you see a gas, you have to tell me what's the temperature of the gas and what's the pressure of the gas, okay? Okay, because it could be anywhere in this one-phase region. You need two quantities to specify where you are. You have to specify the temperature and you have to specify what the pressure is. What if you are in a two-phase situation? If you have a sample, you see two phases. Okay, it's a one-component system. So, for example, let's say you see liquid water and water vapor. Let's say you have that point right here. Then the degree of freedom, or the variance, is C minus P plus 2, would just be one component minus two phases plus 2. That gives you 1. That means you have one independent variable. Look at this case right here, okay, this point. If I specify the temperature, okay, and I say, all right, let's say this is 298 Kelvin, and I see liquid water and gaseous water at equilibrium, then I don't have a choice about what my pressure would be. Okay? Nature already tells me what that pressure is going to be, and that's going to be 23.8 torr. If this was 298 Kelvin, if this was water, okay. So in a two-phase, on the two-phase curves, okay, where you have two phases at equilibrium, you say your variance is 1 by specifying either the temperature or the pressure. The other one's defined. So you have only one independent variable. Now, what if you have three phases at the triple point? At the triple point, so you have your variance is going to be 1 minus 3 plus 2. That's going to be 0. You say a triple point is an invariant point. So this point right here, where the three regions intersect, is an invariant point. That is well defined. You cannot specify what that temperature or pressure is. Nature tells you what that is. It's characteristic of the substance. Okay. Supercritical region, that's a single phase. So you would also need to specify what the pressure is and what the temperature is. Okay. So let's just answer these questions. What are the phases represented by A, B, C, D, E, and F? A and D would be solid, right? E would be a liquid, and B, C, and F would be gases. And all of these points are in a one-phase region, so all of these points would have a variance of 2. Okay, so F in this case would be one component minus one phase plus 2 is 2. Okay. All right. How about this one? Describe the phases represented by points A, B, C, D, E, and F. Okay. Let's look at A. That looks like two solids at equilibrium. Okay, so that's two phases. 1 minus 2, C minus P plus 2 would be 1. So the variance there is 1. By specifying the pressure, you know what the temperature is. If you specify the temperature, you know what the pressure is. Okay, one independent variable. What about point B? Then you have a solid in equilibrium with a liquid there. Okay, and then point E, you have a liquid in equilibrium with a gas. At point D, okay, so those three are two-phase. So A, B, and E represent conditions where you have two phases coexisting. Okay, so the variance for those is 1. Okay, what about point C and point D? Those are triple points, so these have a variance of 0. Okay, all right, so let's take a look at this diagram. Um, At 1 atmosphere, does the substance represented in this diagram sublime or not? What is sublimation? Sublimation is when changing directly from solid to a gas without first turning into a liquid. Well, at 1 atmosphere, room temperature, this is the point, so you would expect your substance to be a solid at room temperature. What happens if you heat it? Then it will turn into a liquid first. Okay, and then you continue heating the liquid, eventually your liquid turns into a gas. So that means this substance is not going to sublime. It's going to melt first before it turns into a gas at 1 atmosphere. Okay, you'll notice that's what happens when the triple point happens to be below 1 atmosphere. But if you have a substance whose triple point happens to be above 1 atmosphere, like for example carbon dioxide. Okay, 1 atmosphere for carbon dioxide, on the diagram for carbon dioxide, 1 atmosphere might be down here. If it's below the triple point, then if you have a solid, if you heat it, eventually it's going to, it's going to change into a gas. This will be a different temperature here. Okay, so this is the temperature where your carbon dioxide would sublime. Okay. And so that's how you would interpret. You can use a phase diagram to predict whether a substance will sublime or not. It would depend on what the external pressure is. So typically we will be at 1 atmosphere pressure. All right. The Clapeyron equation explains the slopes of the two-phase curve. So this slope right here, why is this slope that way? Why is the shape of that curve that way? Why is it sloping that way? And why is this solid curve, why is it steeper than the liquid gas curve? The solid gas curve, why is this steeper than the liquid gas curve? And why is this solid liquid curve very steep? And in the case of water, why does it lean the other way instead of this way? Typically, your solid liquid curve leans this way, positive slope. So all of these have positive slope, with the exception of water, where the solid liquid curve has a negative slope. We can explain all of that using thermodynamics, and it's a Clapeyron equation that summarizes the behavior of these substances. Okay, so the thing to realize is this: at every point in these two-phase curves, you have equilibrium. So let's say this point right here. Okay, you have liquid and gas at equilibrium. Then the chemical potential of the liquid, as we've shown before, must be equal to the chemical potential of the gas at that point. Okay, so the chemical potential of water in the liquid, the substance in the liquid, would be equal to its chemical potential of the gas at each and every point on this curve. Now, at each and every point on this curve, the chemical potential of the solid will be equal to the chemical potential of the liquid. And at each and every point on this curve, the chemical potential of your solid will be equal to the chemical potential of your gas. All right, so let's just examine the liquid to gas curve. Then if I were to move from one point to another, then the change, okay, let's imagine two neighboring points very close to each other. The change in the chemical potential for the liquid as I move from one point to its nearest neighbor would be equal to the change in the chemical potential of the gas, because the chemical potentials would have to be the same at each and every point. Okay, so if you recall, dG is equal to minus S dt plus V dP, and the chemical potential is just the molar Gibbs energy for a gas. Right? So we can put, it's just the molar Gibbs energy for a pure substance. Okay, so we can put a bar on top of your G, that, and dG bar would now be d mu. Okay, so d mu is equal to minus S bar dt. The bar simply means per mole, plus V bar dP. So this thing right here, d mu, then there should be a bar on top of that one, and V bar dP. Okay. So that would be the change in the chemical potential as you move from one point to the neighboring point. All right, so let's do that. For a liquid then, you can say d mu of the liquid would be equal to d mu of the gas as you move from one point to another to the next point on your curve. So you say minus S bar dt for the liquid plus V bar dP for the liquid must be equal to negative S bar for the gas dt plus V bar for the gas dP. Okay? And now what I'm going to do is I'm going to collect all my dTs on one side. I'm going to move this one over to the left. So I have S bar gas minus S bar liquid dt. And I'm going to move these over to the right. So that's equal to V bar gas minus V bar liquid dP. And why am I doing this? Because now I can solve for dP dt. That's the slope of my curve. Derivative of pressure with respect to temperature for the vapor pressure curve. For the liquid gas coexistence curve will just be this. What is this? This is just delta S, right, for vaporization. Okay, and actually we put the symbol VAP in between the word VAP. Delta S vaporization, that's per mole. And this is right here is this delta V, change in volume as a result of the vaporization. So that's delta V bar vaporization. Now these are quantities per mole, but you can actually just use delta S over delta V here because the moles will just cancel out. Okay, so this equation right here, dP dt equals delta S over delta V, that's called your Clapeyron equation. Okay, now since at each and every point on these curves, okay, you have equilibrium, then that means delta G would be equal to 0 is equal to delta H minus T delta S, right? So delta S can also be written as delta H over T. So you can also write your Clapeyron equation, as instead of delta S, you can replace delta S by delta H over T delta V. Okay? Now, let's try to explain now the slopes of these curves based on the Clapeyron equation. According to this, let's look at the solid, why the slopes are positive, okay? Why would the slopes be positive? Remember, going from solid to liquid to gas, those are all endothermic processes, right? So delta H is positive. Okay? And so, so for in the liquid to gas case that we just looked at, right? Okay, then delta H is positive. What's the change in the volume as you go from a liquid to a gas? Delta V will also be positive. You expect the volume of a gas to be much larger than the volume of a solid or a liquid. So that's positive. So you would expect the slope to be positive. Okay? So solid to gas, same thing. Liquid to gas, same thing. Positive slope. Why is the slope steeper for the solid to gas? Well, let's take a look at the entropy instead of the delta H over T. The entropy, solid to gas versus liquid to gas. You expect the delta S here to be larger. Okay? More positive. So you see the slope of your solid to gas coexistence curve is a little steeper than the liquid to gas coexistence curve. Now, why is the slope of the solid liquid curve very steep? so why is this thing right here, why is that very steep? Well, here's one way to think about it in comparison to the slope of the solid of these other two curves, okay? In comparison to the liquid to gas and the solid to gas curves. This is very steep because your delta S from solid to liquid is not going to be as big as going from solid to gas or liquid to gas. So this is going to be small compared to the other curves. And this delta V going from solid to liquid is also going to be very small. In fact, this is very, very small change going from solid to liquid. So you have a very small denominator, okay? And this is actually what will predominate as far as this calculation is concerned. You have a very, very small denominator, hardly any change in the volume going from solid to liquid. So a very small denominator would make this slope very large. You have a very steep slope. Now, how can your slope for water be leaning the other way? Why would you have a negative slope? Well, solid to liquid, we still know that that's going to have a positive delta S, right? Delta H for that is positive also. So the only way it could make it negative is if delta V is negative. And in fact, that is the case for water. So water is an exception, okay? Typical delta V would be positive. Going from solid to liquid, typically the volume expands. But what do you remember about ice? Ice floats on water, right? So volume of ice is greater than the volume of the liquid. So if you go the ice for the same amount, right? So that means if you go volume of liquid minus volume of ice, that's your delta V, is going to be a negative number. And that's why the slope for water, for the solid liquid curve for water is negative. Okay? So that's the Clapeyron equation. Now, when we're dealing with the solid to gas and liquid to gas equilibrium, okay, we can simplify the Clapeyron equation. We can add an approximation, and that approximation has to do with the fact that the volume of the gas is going to be much, much larger than the volume of the solid or liquid that it comes from. And just to give you an example, if you remember what water, okay, density of water is about 1 gram per mil, liquid water, right? So a mole of water is 18 grams, right? So that's about 18 mils. Compare that to a mole of water, 1 mole of water at STP. Okay, what's a mole of water at STP? 22.4 liters. So that's 22,400 milliliters. Okay. So what's the volume change if you go from 18 mils to 22,400? The 18 mils is negligible, right? So what we're saying then is that the delta V is essentially just the volume of the gas. Okay? So dP dt, delta H over T, delta V, that's your Clapeyron equation. When you make this jump right here to this approximation, you now have what's called, you're on your way to deriving what's called the Clausius-Clapeyron equation. All right. So volume of a gas, if it's ideal, if you remember, PV equals nRT. So volume per mole, which is V bar, is equal to RT over P. So what I've done here is I've replaced the molar volume of the gas by RT over P. And let's rearrange that equation. What do we get here? We say dP dt equals delta H over RT squared and then times P, right? And I'm going to separate my variables. Let's call this differential equation. I'm going to write dP over P on the left is equal to delta H over R, and then you have dt over T squared on the right. Okay? All right. Now, I integrate both sides. If P1 is the vapor pressure at temperature T1, and P2 is the vapor pressure at temperature T2, then what's integral of dP over P? Integral of dP over P is ln of P, evaluated from P1 to P2, so that's ln of P2 over P1 equals. If I were to assume that my temperature interval is small enough so that throughout that interval delta H will hardly change, I can factor delta H out as a constant, and so I can also factor out R since it's a constant. What's integral of dt squared over T? Dt over T squared, sorry. What's the integral of dt over T squared? Well, that's the integral of t to the negative 2 dt, right? So t to the negative 2 plus 1 over negative 2 plus 1 is just negative 1 over t, right? So this is just negative 1 over t. I'm going to put the negative over in front here, and then I'm going to evaluate this from T1 to T2. So what I have now is this equation right here. ln of P2 over P1 equals negative delta H over R, 1 over T2 minus 1 over T1. What is this delta H? That's the enthalpy of vaporization. We're going from liquid to gas. Okay, if you're doing liquid gas equilibrium, if that's the if the pressures here are the vapor pressure of a solid, then that would be the delta H of sublimation. Okay, so that allows you then, so this is your equation right here, your Clausius-Clapeyron equation. Oops, what just happened? Clausius-Clapeyron equation right here. Is the final result over here. Okay, so if you were to do that, get data at two different temperatures, the vapor pressure at two different temperatures, you can solve for delta H bar. Okay, so that's delta H per mole for vaporization or sublimation would be negative R. Can rearrange that to be negative R times natural log of P1 over P2 over 1 over T1 minus 1 over T2. Okay? Now, graphically, what does that look like? If you were to plot natural log of P versus 1 over T, okay, so this is ln P1, 1 over T1, right? So we call this 1 over, if you were to call this 1 over T1 ln P1, and this other point right here is 1 over T2 ln of P2, then what we did here is just calculated the slope of that graph, right? So the slope is just of the graph is just this one right here. Because what's the slope? ln of P2 minus ln of P1 over 1 over T2 minus 1 over T1, or the other way around. But what's ln of P2 over P1? That's ln of P2 over P1. Okay, so if you have experimental data, then 2 points determine your line and will get you the slope. If you want more reliable information, of course, experimentally collect more data points. So you plot natural log of P versus time versus 1 over temperature, and you plot ln of P versus 1 over T. Draw the best fit line, and so delta H vaporization or sublimation will just be negative R times whatever the slope is. Okay, so that's what you can get from the Clausius-Clapeyron equation. Okay, so far we've been assuming that we have a pure substance and we have our sample in an enclosed container. So for example, if you have water here, liquid water, let's say, that the only thing we have over here is gaseous water. you don't have any other gas in there. But in a typical scenario, you would have, you might have some air in there, right? So what would be the effect of air on the observed vapor pressure of the water? Okay, so let's make it more generic. Let's just call our substance A instead of water. So if there was just pure A, okay, so let's set up the problem this way. Let's say you have pure liquid A in equilibrium with a gaseous A, nothing else there. Then the pressure of A here, we're going to call it P sub A star. Okay, the star indicates that we're dealing with a pure vapor. We're going to compare that with the situation where you have, instead of just pure A, okay, you still have pure A in the liquid, but instead of pure A in the gas, you have A in the gas plus some inert gas, other gas like air. Okay, so the pressure, partial pressure of A here, okay, what will it be compared to the partial pressure in the pure sample, the one that doesn't have any inert gas? So we're going to call that P sub A, partial pressure of A in the presence of an inert gas. Okay, so the total pressure will just be partial pressure of A plus the pressure of the inert gas. Okay, in this situation right here. And so like I said, let's try to figure out how the presence of the inert gas will affect P star A. Okay, how will it affect the partial pressure of A? All right, so let's analyze this using the concept of chemical potential and how it depends on pressure. All right. Now, in your pure sample, okay, at equilibrium, so if we are at equilibrium, then the chemical potential of A in, okay, I'm doing solid here, so let's make this a solid. Doesn't really matter, solid or liquid. Okay. Now let's just assume we're dealing with a solid to gas equilibrium here, and the same analysis can be done with the liquid. Okay, so chemical potential of A in the solid, in the pure solid, okay, would be equal to its chemical potential in the gas, in this situation right here. But earlier we said that the chemical potential of a gas, if it's behaving ideally, would be whatever the standard state potential is at 1 bar plus RT ln pressure of the gas, which in this case is going to be PA star, okay, over P naught. P naught is 1 bar, and mu naught is a chemical potential at 1 bar. We learned that in an earlier lesson. Okay. Now, in the presence of the inert gas, with the inert gas present, okay, chemical potential of A in the solid, okay, will not be the same as mu A star, because mu A star is subjected to a pressure of only PA star. This is subjected to a higher pressure. Total pressure here is P. Okay, so the chemical potential would be chemical potential of A, pure A, subjected only to PA star, but there's going to be a change in the chemical potential. Why is that? Well, mu A in this sample with the inert gas minus mu A in the sample with no inert gas, that's just delta G per mole, okay? That would result from an increase in the pressure on the solid. Okay, if you remember, G bar is just mu. But here we're dealing with the same temperature, so delta G, remember dG is equal to negative S dt plus V dP. So d mu, or dG bar, is minus S bar dt plus V bar dP. Since we're dealing with constant temperature here, we're not interested in a different temperature, we're just changing pressure. D mu is equal to V bar dP, so delta mu, the change in the chemical potential, will just be the integral of V bar dP. But V bar is the molar volume. volume per mole. What happens to the volume of a solid or a liquid if you pressurize it? Well, in a solid or liquid, your molecules and your atoms are as close as they can be, just about. So higher pressure is not going to change the volume by much. Okay? So for practical purposes, we can factor out V bar out of your integral. It's not going to depend on pressure. So that's V bar times integral of dP from, you're going to integrate the pressure increase from PA star to P. Okay? We're comparing the scenarios where in the first case it's subjected to a pressure equal to PA star, in the second case it's subjected to a pressure P, total P. So integral of dP from P star A to P will just be equal to V bar times P minus PA star. And that's what we have up here. Okay? So V bar is the molar volume. So V sub m is the same thing as V bar. All right. So we've established that. Okay. So this one and that one. Now, what is the chemical potential of A in the gas phase over here in the presence of the inert gas? Well, chemical potential of A would be the standard chemical potential plus RT, Ln, whatever its partial pressure is going to be in this sample over P naught. Okay? So that's just the formula for a chemical potential, assuming it's behaving ideally. The ideal gas is ideal. Now, in this sample right here, the chemical potential of A, since this is at equilibrium, okay, then the chemical potential of A in the solid must be equal to the chemical potential of A in the gas. So these two, we say, are equal. All right. So how can we show then, from all of these, okay, you should be able to show this relationship right here. And let's do that. We say that, okay, mu A solid, okay, is mu A star, mu A solid star, plus molar volume P minus PA star. I'm going to make the substitution here. Mu A star is equal to this thing right here. So I'm going to substitute it for there. So I'm going to say mu A solid equals mu A solid star, which is mu naught now, plus RT Ln PA star over P naught plus molar volume, I'm going to call that V bar instead, P minus PA star. Okay? And that's equal to, that is equal to mu A gas, which is mu naught plus RT, this thing right here, RT Ln of PA over P naught. So these two are equal. If that is the case, we can then say, oops, that, okay, mu naught plus RT Ln PA star over P naught plus V bar P minus PA star, let's see, must be equal to the one down here, which is mu naught plus RT Ln PA over P naught. So we can cancel mu naught and combine the log terms, and we end up with RT Ln, okay, I'm going to move this one over to the other side, okay? So I'm going to have V bar P minus PA star equals RT ln PA over P naught divided by PA star over P naught. Okay. Because if you remember, ln x minus ln y is just the same thing as ln of x over y. Okay, so V bar P minus PA star equals RT natural log of PA over PA star. Okay, your P naught is going to cancel out. And so I can divide both sides by RT and take the inverse log, or I can just say ln of PA over PA star, divide both sides by RT, is V bar P minus PA star over RT. And I can say that P over PA star is equal to V bar P minus PA star over EXP. Okay, so it would be the inverse log EXP. So that's how you would calculate the change, the ratio of the new pressure of A to the original vapor pressure. Okay, so to what extent, let's predict. P is a larger number than PA star, right? We raised the pressure due to the inert gas. So this whole thing right here is a positive number. So you have E to a positive number. Okay, and so like if this was a positive number, then you would expect PA over PA star to be greater than 1. So you would expect an increase in the vapor pressure of your solid or your liquid in the presence of the inert gas. But to what extent? Let's do an illustrative calculation. Let's say your water, P star for water is 23.8. Then P over P star would be E to the molar volume, P minus P star over RT. So you have 23.8, let's say, plus we have enough air to make it 1 atmosphere total pressure. Okay? So to what extent will this vapor pressure be affected? Well, if you did that calculation, you plug in the numbers. Molar volume of water is 18 mils per mole. You plug that in. And your pressure is 1 atmosphere. So that's 760 torr, right? Or 1 atmosphere. And then P star would be 23.8 torr divided by 760. That would make it atmospheres. You plug in your R, which is 0.08206. 0.08206 liter atmosphere per mole per Kelvin, and you plug in your T, which is 298 Kelvin, and you'll find that P over P star is 1.00071. Okay, so you're looking at a 0.071. Okay, you're looking at percent increase in the vapor pressure. 0.0071 over 1.0000 over 1, so times 100%, so that's 0.071% increase in the vapor pressure. Not a whole lot, okay? So what is 1.0071 times 23.8 torr? That's just 23.81 torr. Within the sig figs, it's still going to be 23.8 torr. Now, this calculation we're doing assumes that there is no interaction between the inert gas, that's why it's called inert gas, and the molecules of the water molecules, the molecules from your solid or your liquid. Okay, so the actual vapor pressure in the presence of inert gases could actually be much higher than what we might predict with this equation. If there's a strong interaction, for example, you can have what's called gas solvation. So the molecules of what we would call the inert gas would actually interact with the molecules of your substance, okay, and that could lead to a higher vapor pressure of the substance. And one application of this, for example, is in the decaffeination using supercritical CO2. Okay, so you have CO2 would end up basically, you can think of it as dissolving the caffeine from the coffee beans into the gas phase. It would increase the vapor pressure of caffeine.